Okay, so we're going to look at systems of linear equations today. Yesterday at the end of class, we looked at systems of nonlinear equations. So you probably have looked at working with two equations and two unknowns before. And there's three possibilities that can happen when you're dealing with two equations and two unknowns. And the first thing that could happen is graphing this. This works. Start over. So graphing this, what would happen when you graph the two lines, somehow when you graph them, they're going to intersect in one point. So if this happens, the solution is the point of intersection. And there's only one solution here, and this is called an independent system. Okay, so another possibility, if you went and you graphed your two equations, it is possible that when you graphed them, they actually were the exact same line. So any point that lies on the line is going to be a solution to the system. So any point on the line is a solution. This is called a dependent system. So both independent and dependent, you might also hear that they're consistent systems, meaning that they have a solution or solutions. The other one is an inconsistent system. And what would happen is when you graph these, they ended up being parallel lines, but with different y-intercepts. And so they're never going to intersect one another. And so there's no solutions. Okay, so this is what's happening graphically if you're dealing with two equations and two unknowns. And there's a couple different ways that you can solve when you're solving them algebraically. Graphically, technically, is not the best way. You can use that method to solve these systems. It's just hard to see if you don't have the technology and you're graphing it by yourself, especially if that point of intersection is not at an integer. So maybe it was at, 2/3 or something. That would be hard to see that on the graph. So solving it algebraically, though, you're always going to get an answer if there is one that exists. And there's two ways to solve it algebraically. You can either solve it using what is called the substitution method, and that's where you're solving for one of the variables in terms of the other and plugging it back in. And then the other method is called either the addition or elimination method. And that's when you're summing two of the equations and you're manipulating it sometimes to multiply one of the equations by some constant and the other equation maybe by another constant, so that when you sum them together, one of those variables disappear. And then you have one equation with one variable to solve for. So this is all stuff that should be reviewed. So I'm just going to kind of quickly, that's why I'm quickly talking through this and not writing this down. But let's go through a couple of examples, and then let's move to 3 equations and 3 unknowns. So the goal is, once we get to 3 equations, 3 unknowns, I'm going to teach you a different method to solve this, and it's using matrices. Okay. So let's say you had the following system of equations, and you have x plus 3y is equal to 5. Is one of your equations, and you have 2x minus 3y equals negative 8. Okay, so first thing you want to do is determine which method you want to use. To me, everything, my variables are on one side and the constants are on the other. And I noticed right away, if I sum both of these equations, my variable of y would cancel out and I can solve for x. And so to me, the addition method would be the easier way to do this. And so if and I'm going to start doing this notation because we're going to use this while we're doing matrices. And so I'm going to explain what I'm doing, what work I'm doing. I'm going to call this first equation row 1 and this second equation row 2. And I'm going to denote that with a capital R and then the subscript of what row or equation it's representing. And so right now, all I'm going to do is I'm going to add row 1 plus row 2. Because I can just do this, I can just sum it right here. So x plus 2x, this gives me 3x. 3y minus 3y, those cancel, is equal to 5 minus 8, which is negative 3. So usually when we're doing this notation, when I'm doing this notation, the last one I'm using in this sum or difference, I always do sum of equations. This is the row or equation I'm changing. So I'm changing row 2 with this sum. So technically, you have we have a new system here, and I'm not going to always write this, but this is what you're doing. You're basically using these couple rules that you can use in order to rewrite equivalent systems that will have the same solution. So I just used my first equation to manipulate my second equation, but my first equation is going to remain the same. So basically I have x plus 3y equals 5. And now my new row 2, or equation 2, is 3x equals negative 3. Well, it's in the way that we can solve for x in the second equation. So technically what I'm doing to solve for x here is I'm taking 1/3 times my second row. So if I multiply 1/3 by my second row, well, 1/3 times 3x, this is just x, is equal to 1/3 times negative 3 is negative 1. So again, I have a new system. I didn't do anything to my first row. I still have x.
Where did you get the 1/3 from?
So I'm trying to solve for x here. And so one way I can think of it is multiplying both sides by 1/3. So it's just the reciprocal of 3.
Okay.
And so if I do that, then I get x equals negative 1. And so with this new system, we can use substitution. We're going to back substitute. To find y. So if I go back into this first equation and wherever I saw an x, I replaced it with a negative 1. we can figure out what y has to be. So if I do that, I get -1 plus 3y equals 5. So solve for y. And we add 1 to both sides. We get 3y equals 5 plus 1 is 6. Divide by 3, or same thing as multiply by 1/3. We get y is 2. So our solution, if we graphed those two lines, we would see that they were intersecting at the point -1, 2. Okay, so there's 3 things that we can do to take a system of equations and manipulate it to be an equivalent system where they have the same solution. And so we were kind of doing this right here in some of those. And so operations, for systems of equations. We can do the following and get equivalent solutions. So sometimes it's helpful just to move your equations around. So interchanging we didn't do that this time. Equations. This is also going to hold true when we're dealing with matrices. So I'm just going to put in here interchanging equations or rows. We can rewrite an equivalent system by multiplying an equation or a row by a non-zero constant. And so that's kind of what we were doing right here when you were asking where did that 1/3 come from. So we were multiplying this equation by a non-zero constant. So another operation that we can do to get an equivalent system is multiply an equation or row by a non-zero constant. And then the last operation that I can do is I can sum 2 equations together, or I can sum a multiple of one equation to another equation and replace it. So summing a multiple of one equation or row with another. And that's what our first step was. We basically were just summing the multiple of 1 times equation 1 plus 1 times equation 2. Sometimes we want to do it other than 1 if it's not the same. Our goal for trying to do the elimination method is to get opposite coefficients in front of the same variable. So 3 and -3, those are opposite coefficients of one another in front of the y. So that when we sum them, one of them will go away. So if you have the system, let's say 2x plus 4y is equal to 2/3, And we have the system, or the next equation is 3x minus 5y is equal to negative 10. Okay, so again, I have it set up in the form that I can do the addition method or elimination method, whatever you want to call it, easily, where if I had to use the substitution method, I'd have to get one of my variables alone in terms of the other one and then go back and plug it in. And it's not easy, or doesn't look easy, to get x by itself or y by itself. I would have to deal with a lot of fractions, and I don't want to deal with that. I could, or we could, if we wanted to, we could get rid of this fraction in the equation 1 by multiplying this by the LCD, which is just 3. So maybe doing that. So I'm going to do 3 times row 1. And so if I multiplied everything through by 3, that would change my equation to 6x plus 12y is equal to, the whole point of me doing this was so that the denominator would cancel, is 2. I didn't do anything to equation 2, so I'm just going to rewrite it. And so now looking at this, I can either get the same coefficient, well, opposite signs though, in front of the x or the y values. So when you're determining that, you're basically looking for if this was your denominator. Another way to say it, your least common multiple. So what is the smallest thing they both divide into? And so that would just be 6 here, where if I had to look at the bigger numbers, 12 and 5, that wouldn't happen until 60. So I'd rather deal with getting both of these. And so technically what I'm going to do is I'm going to take this first row, row 1, and I'm going to add it to, in order to get this to be a negative 6, I would have to multiply this row 2 by negative 2, row 2. Okay, so doing that, if I rewrote this, I have 6x plus 12y equals 2. Multiplying this by negative 2, everything in that second equation, I get negative 6x. Negative 2 times negative 5, that's plus 10y, equals positive 20. Right. Nope. Yeah. So summing this up, I get my x's cancel, whole point of that. 12y plus 10y is 22y equals 22. So from right there, we can figure out what y is. Y we can see is 1. So it doesn't matter which equation you choose, but you need to go back into one of these equations and determine what x is by plugging in what y is. So we're going to back substitute. And so if we do that, we get 3x minus 5 times y, which is 1, equals negative 10. So we get 3x minus 5 equals negative 1. Add 5 to both sides. Oops. This should have been negative 10 right here. Didn't copy it down right. Negative 10 right there. So adding 5, we get 3x equals negative 5. And x then is equal to, divide both sides by 3, negative 5/3. So the solution is at the point negative 5/3, comma 1. Okay, so I can always check this It would have to work both X and Y in order for this to be a solution, would have to make a true statement for each equation we go back and plug this in. Okay, so if we start with more than two equations, two unknowns, let's see if I can pull this up real quick. Then we're dealing with graphing in 3D. So it's a little more difficult to kind of think about what's going on. So that's where I pulled this picture from the internet. And so one case scenario, it's a consistent system, and you're going to have a 1 point as your solution. And so basically when you're graphing it, I think of the plane as a sheet of paper that just kind of goes on forever in that one direction. Other possibility is that you have every point on a line is a solution. It could be possible that all three pieces of paper, all three planes are the same, exact same thing. So any point on that plane is going to be a solution. If the planes are parallel, there's no solution. And so notice here where, you have a vertical plane and then you have two horizontal planes. And so there's not an identical place where all three of these are intersecting. And so there's no solution. And same sort of idea with the picture F, where you're having kind of that triangle shape. And so there's no place where all three of those planes are intersecting. And so this right here, these are all examples of three equations and three unknowns. Okay, so matrices are kind of a cool way to be able to keep everything kind of organized while you're doing these order of operations on these systems of equations to manipulate it to get your solution. So let's I'm going to just bring in, I think, matrices right away. And so let me kind of get you some terminology. And so what we're going to be doing is we're going to be taking a system of equations. So for example, let me just pull one out. Let's say we had one equation is x minus y plus z is equal to 10. We have 3x plus 3y equals 5. And then the last equation is x plus y plus 2z is equal to 2. Okay, so let me right now hopefully save you a lot of heartache. So first thing you want to do is actually go in and you want to make sure that you had written this equation down right, because if you didn't, then then you got to start all over. And so sometimes one of the main errors I see is we don't copy it down right to begin with. And so let me just go back in and I'm just going to reread it and make sure I have it. So x minus y minus z equals 10. So right there, I just noticed I did not copy that down right. And so I'm going to put a minus here. So minus z equals 10. You know what? I'm copying. Sorry, looking at the wrong problem. Let me go to the right problem. Negative x minus y plus z equals 10. That was right. 3x plus 3y equals 5. That was right. X plus y plus 2z equals 2. Okay, so I copied it down right. So once you have your systems of equations, before we can put this in what is called a matrix, you want to make sure that all of your variables of x line up, all your variables of y line up, vertically z, and then you have an equal and all your constants are on the other side. So when you put this in a matrix, all you're doing is you're just writing down the coefficients, the numbers in front of your variables in that horizontal row. And so my first row of this matrix is just going to be numbers, and my coefficient in front of x is 1. So I'm going to have a 1. My coefficient in front of y is -1, so -1. Coefficient in front of the z is 1. And then to denote that there was an equal sign here, we're just going to put a dotted or a solid line. And then we have 10. So now that was just my coefficients and constant of my first equation. And now I'm going to my second equation, which is going to be my second row of my matrix. And so I have a coefficient of 3, 3. There's no z here, so I'm going to put 0 and then 5. So looking at the last equation, my row would be 1, 1, 2, 2. So this is called a augmented matrix. So when we're working with this matrix, at the end, anything that's in this last or this first column represents the numbers in front of our x. Anything in the second column, those are the coefficients in front of y. Anything in this third column are the coefficients in front of z equals some number. So if we work with this, our basic goal is we want to know what x, y, and z are. And so what we're going to try to do is we're going to try to manipulate this to look like where there's ones in this main diagonal and zeros everywhere else in this matrix. So we're going to manipulate the augmented matrix to have ones in the main diagonal and zeros above and below the ones where possible. Right, I can get a 0 in front of this. And how we denote where our entry is, we always denote the entry by, and it's not too important in this class, but we always do it by row and then column. So this 1 here is in the first row, first column. This -1, it's in the first row, second column. This 1 is in the first row, third column. So if I went down here to this 2, this is located in the 1, 2, third row, and then the third column. But that's not, you're not going to be tested on that. Basically, you just need to know that you want ones in this main diagonal and zeros anywhere below or above that if possible. Okay, so when we're manipulating this, and this is what it's going to look like, and it could be bigger than this or smaller than this, but basically what we're trying to manipulate, it just showed you kind of, was 1, 0, 0, 0, 1, 0. There could be more things in here. That's why I'm doing the ... Could be bigger than a 3 equations, 3 variables. So ... Okay, so basically, if we were able to do this where that 1 is in the main diagonal, and this was our value of x, this would be saying, well, then x has to equal a. If this was my column that represented all the coefficients of y, and I only had one term that had a y in here, because these are 0y, 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 this would be saying y would have to equal b. And so this is why the goal is going to help us when we're looking at trying to figure out what our solution is. So we can do the same exact thing that we were doing when we left the variables in there when we were dealing with the systems of equations. You can interchange your equations around, or rows. You can multiply an equation by a non-zero constant or row, or you can sum it with a sum of a non-zero constant of another row in itself, or multiple. Anyways, when you're doing this, it's very, very helpful if you keep things in order. If you don't keep things in order, you can be undoing what you had just done or just making a mess of it. And so when you're working with these matrices, it's always helpful to work column to column. So working with matrices is just the plural for a matrix. So working with matrices, to solve a system of equations always work column to column. So working with column 1, then column 2, then column 3, etc. It's also usually best if you get that number, what you want it to be, in that column of 1. And we call this one the leading one. So make the entry in the column a 1 where you need it. So once you get that number of 1, then you can get rid of the numbers above that 1, if there are any, or below that 1, if there are any, by just multiplying by the opposite of the number you're trying to get rid of. So use that 1 to get rid of all the entries above and below. So part of this, which I've just pulled out, was just an example, and it just wanted us to take that example and put it in augmented form. I'm worried that if I try to solve this, this might be a really ugly one, so I'm just going to kind of go and do a couple more examples and pull one out that the book actually gave. Before we even jump in, some of the exercises, we're just getting used to the notation. When I'm doing this, I do it a little differently, and I always do, some row A plus some row, whatever it is, B. The second one is always the one I'm changing. That's not always the case on how they're writing it or other people do it. So for instance, let's say it says write the system of equations corresponding to each augmented matrix, then perform the indicated row operations on the given augmented matrix. So for instance, if they had a matrix where the first row was 1, -3, -3, and then 2, -5, -4. And so the directions was saying row 2 is equal to -2 row 1 plus row 2. Oops. So that's what the book says. I would have just written this -2 row 1 plus row 2. So while we're doing this, we can actually do this without writing things down again over here. So I am not changing my row 1. I'm just using my row 1 to manipulate row 2. And so sometimes it's helpful to write down the rows that you're not changing in your matrix. And so I'm not changing row 1. I have 1, -3, and then the augmented -3. And so now let's multiply row 1 by -2 and add it to row 2. So if I do -2 times this 1, that's -2, plus the 2 below gives me back 0. Okay, and so -2 times that next entry in that row, so -2 times -3 is 6, and 6 minus 5 is 1. And then -2 times -3 here is +6, and 6 minus 4 is 2. Okay, so let me take a pause for a sec. Okay, so let's look at one more example before we jump in and actually solve one of these using matrices. So looking at the following matrix, the first row we're given is 4, -3, -1, and then a line, and then 2. Second row, we have 3, -5, 2, and 6. And the third row, we have -3, -6, 4, and 6. So it actually has multiple directions. Row 1 is equal to negative row 2 plus row 1. And then row 3 is equal to row 2 plus row 3. So they're pretty much kind of writing it like I would do it. This is the row I would be changing, so that's what I write second. This is the row I'd be changing. So notice that in here, they're not changing row 2 at all. They're using row 2 to help us manipulate row 1 and row 3. And so let's go back in here and let's copy down what row 2 is, because we're not changing it, we're just using it. So we have 3, -5, 2, and 6. Okay, so matrix is going to help us keep it in order. So we're taking the negative of row 2, so negative of row 2, and then summing it to the row 1. So -3 plus 4. So -3 plus 4 is 1. So now take the negative of the next entry, so in row 2, so negative of -5 is 5. 5 minus 3 above is 2. Negative of 2, so -2 plus the number above, -1 is -3. Negative of 6 So -6 plus the number above 2 is -4. So now we're going to do the same thing, but this time it's just telling me to add my row 2 plus my row 3. So I don't have to multiply this row 2 by anything. I can just sum it. So I have 3 minus 3 is 0. 5 minus 6 is -11. 2 plus 4 is 6. And 6 plus 6 is 12. So any questions on what we had just done with the matrices or how we're doing these row operations? Take off this and maybe write a little differently. Okay, so let's try one.
Not.
Can you guys hear me still? Okay, good. Yay. Okay, so let's look at an example. I'm going to grab one more page just because things are getting all small. So we're given the following. First equation is x minus 4y plus 2z. This is equal to -9. So second row or second equation is 3x plus y plus z is equal to 4. And the last one is -2x plus 3y minus 3z is equal to 7. Okay, so let's use matrices to help us solve this. So first step would to be just rewrite this as a matrix. And so our first row is just the coefficients in front of our variables and then our constant. They're all lined up how we need it, or we'd have to manipulate it first. And so my first row is going to be 1, -4, 2, then I'm going to put a vertical line, and then -9. My second row is 3, 1, 1, and 4. My third row is -2, 3, -3, and 7. So again, we're going to work column to column. And we want to get that one where we want it in that main diagonal, and it's already done so. If it wasn't, I would either multiply that by a non-zero constant so that I would make it a 1, or I could interchange rows. I could change it with a sum of another, but it's already where we want it, so that's nice. And so now we're going to use this 1 in that row to get rid of the numbers below. And so I know if I multiply 1 by -3 and sum it to this second row, that 3 would go away and be a 0. So I'm going to look at taking -3 times my row 1, and then I'm going to add it to my row 2. So again, I'm not changing my first row, and I'm just using it to manipulate the others. So I'm going to just rewrite my row 1 down so I don't get confused. So 1, -4, 2, and -9. Okay, so now we're going to take -3. We're going to multiply it by each entry in the first row and sum it to the entry right below it. So -3 plus 3, that gives me 0. And that was the whole point of doing that. -3 times this -4 here, that's a positive 12. 12 plus 1 is 13. -3 times 2 is -6. -6 plus 1, -6 plus 1 is -5. -3 times -9, that is 27. 27 plus 4 is 31. Okay, so this is where just making a little teeny error with your arithmetic can get screwed everything up. And then trying to find that error is hard. And so this is where having, these directions of what you were doing is helpful. And I didn't do it, and I told you guys to do it. I'm going to go back and I'm just going to go make sure before I even do any more work that I wrote this down right. That would be awful. X minus 4y plus 2z equals -9. That's good. 3x plus y plus z is 4. That's good. -2x plus 3y minus 3z plus 7 is good. Okay, I'm fine. So we got the 3 as a 0, how we wanted it. And so now let's get rid of the number below that 3, that -2. We want to make this a 1. I'm sorry, we want to make this a 0. We want to use this 1 in this row and multiply it by something so that when we sum it to this third row, this -2 goes to 0. So if I look at 2 times row 1 plus row 3. So 2 times 1 is 2, minus 2 is 0. 2 times -4 is -8. -8 plus 3 is -5. 2 times 2 is 4. 4 minus 3. 4 minus 3 is 1. 2 times -9 is -18. -18 plus 7 is -11. Okay. I know that I'm done with my column 1 and I'm moving to my column 2. I'm just not happy because it's not coming out very clean and I don't want to deal with fractions. So I have to go back, and now I'm working with my next column. I usually want to get this to be a 1 here so that I can manipulate it and get zeros above and below using that 1. I notice if I multiply through by 1/13, that is going to give me fractions, and then when I'm summing things with fractions, I have more error. So I'm looking to myself to see if there's any way I can manipulate, and I actually just found it, yay. Doing some sum of another equation and this to make 1. The problem is if I use my equation in row 1 to do that, so I could multiply that by 3. 4 times 3 is -12 plus 12. -12 plus 3 is 1. The thing is, if I did that, I would get a number where I just put a 0, and I don't want that anymore. And so I also noticed that, 5 times 5 is 25, and 2 times 13 is 26. So I could do, how about, and that's gonna, 0 plus a 0 here is just gonna keep a 0 where I want it. So that would be 5 times row 3. That would give me a -25 plus 2 row 2. Okay, so before I even do any of those changes, I'm going to go back in and I'm going to rewrite the rows that I'm not changing. I'm not doing anything to my row 1, so let's rewrite it. 1, -4, 2, and -9. I'm really not doing anything to my row 3. I'm using it, but I'm not changing it. So 0, -5, 1 and negative 11 for my row 3. Okay, so 5 times 0 is 0, plus 2 times 0 is 0. So I have a 0 here. 5 times negative 5 is negative 25. Negative 25 plus 26 is 1. The whole point of us doing that was to get that 1. 5 times 1 is 5, and then this is going to be 2 times negative 5. So 5 minus 10, 5 minus 10 is negative 5. And then 5 times 11, that's negative 55, plus 2 times 31 is 62. 62 minus 55 is a 7 in here. So we got the 1 where we wanted it. We had to do some manipulation to not deal with fractions, but we did it. And so now we're going to use this row 2 to get rid of the entry above that 1 and below that 1. And so I notice if we take 4 times row 2 and add it to row 1, that would cancel out. So we're going to do 4 times row 2 plus row 1. It's okay. Let's also look at the other one. So bottom row, if I multiply the second row by a 5 and add it to the third row, so 5 row 2 plus row 3. So we're just using row 2 to manipulate row 1 and row 3. So 0, 1, negative 5, and 7. Our new row 1, so 4 times 0 is 0, plus 1 is 1. 4 times 1 is 4, plus negative 4 is 0. 4 times negative 5 is negative 20. Negative 20 plus 2 is negative 18. 4 times 7 is 28. 28 minus 9 is 18. I meant to do that black, but that's okay. I guess it's not a big deal. And now we want to get our new row 3. So our new row 3, 5 times row 2, 5 times 0 is 0, plus 0 is 0. 5 times 1 is 5, minus 5 is 0. 5 times negative 5 is negative 25. Negative 25 plus a 1, that would be negative 24. 5 times 7 is 35. 35 minus 55 is negative 20. Did I do that right? Oops, something's wrong. I did it wrong. Right, 5. I'm 5 times row 2. So 5 times row 2. 5 times 7 is 35. Plus row 3, which is negative 11, which is 24. There we go. Okay, so we did what we needed to for our column 2. So now you can go to our next column. And getting to the next column, we want to get that 1 where we want it. That's the easiest thing to do, or the best thing to do. And then once we get this to be a 1, we're going to use that to get rid of the numbers above. Well, notice if you multiply this third row by negative 1 over 24, that would get us a 1 where we want it. So if I do negative 1 over 24 all times row 3. So 0 times anything is 0. 0 times anything is 0. Negative 24 times negative 1 over 24 is the 1. And negative 1 over 24 times 24 is negative 1. technically didn't change anything, or we didn't change anything else, so just recopy it. So 1, 0, negative 18 and 18, and 0, 1, negative 5 and 7. So we're going to use this 1 in row 3 to get rid of all the numbers above. So we're actually just using row 3, but we're not changing it. So row 3 is 0, 0, 1, negative 1. So I notice 18 times the first row, times the third row, add it to the first row, that would get me a 0. So 18, row 3, plus row 1. So 0 times anything is 0, plus 1 is 1. 0 times anything is 0, plus 0 is 0. 18 times 1 is 18, minus 18 is 0. 18 times negative 1 is negative 18. Negative 18 plus this 18 above is 0. So now let's get rid of this negative 5 in row 2. So 5 row 3 plus row 2. So we'd have 0, 1. Well, 5 times 1 is 5, minus 5 is 0. 5 times negative 1 is negative 5, plus the 7 above is 2. So we did it. We got 1s in our main diagonal. We got 0s above and below. And so now we can basically just read off our solutions. This was our column for x's. This was our column for y. This was our column for z. So that first equation reads 1x plus 0y plus 0z, so I don't have to write it, equals 0. The second row, the equation is 0x plus 1y plus 0z equals 2. And that third row is 0x plus 0z, 0x plus 0y plus 1z equals negative 1. So we have our solution to our original system. And it's a point, x, y, z. So 0, 2, negative 1. So again, it's really helpful to be able to write down, and it's really easy to do an arithmetic error. And that's why I was like, that distraction with my daughter talking was hard. Because I knew if I made a little mistake, it's hard to figure it out. These are a pain to grade. And so that's why I really want you, or I won't take long. I won't give you very many points. So make sure you're writing out what you're doing. So if you didn't get it right, I can figure out or try to figure out where it's wrong. We can always test these. It have to work for all 3 equations. So if I plug in 0 for x, 2 for y, and negative 1 for z, all of these should come back true. So that would be 0, 2 times this, that would be negative 8. Negative 1 times z. Uh-oh. I already have a problem. Okay, 2. Right, because if I plug in negative 1 in here, this gives me negative 2. Does that equal negative 9? No. So I know I did something off. I would now just go back and I would just start looking. Did I copy it down right? 1, negative 4, 2, negative 9, 3, 1, 1, 4, negative 2, 3, negative 3, 7. So I copied it down right. Then I would look at, okay, I was using this first row. I copied it down right. Now I can just check my work. So -3 plus 3 is 0. This is 12 plus 1. That's 13. -6 plus 1, that's -5. So far, so good. This is 20. -3 times -9 is 27, plus 4 is 31. And then I'd do the same thing. So it was 2 row 1 plus row 3, that's 0. -8 plus 3 is -5. That would give me 4 minus 3 is 1. -18 plus 7 is -11. So far, so good. This is where I could get off. This is where I manipulated it. So -5 times this row. So that's -25 plus 26 is 1. This is -5. There it is. It's this culprit. So 5, maybe. So 5 times, no, it's not.
Is it the 4 row 2 plus row 1, the black? Because
be.
I got 1, 0, -18, and I got 19 instead of 18.
Okay, so let me check that one. So 4 row 2, so that's -20, that's -18. 4, is this a 31 still? What was that? Nope, something. What was this number? I accidentally erased it.
It's row 2 from the previous, so would it be 7? It would be 0, +1, -5, and then the constant is 7.
Thank you. Okay, so 4, so that's for, that's -16. Where am I at? I'm changing row 1. So that's 4. This is -20. That's right. 4, that's 28. 28 minus 9. That's it. That's it right there. Thank you. So this is right here is 19. We would have gotten there. It just would have taken a while. So this right here is 19. This right here is 19. It's going to be here where it's changed. So when we took 18, so this is 18 minus 18 is 0. And this is -18 now plus 19. So that would be a 1 here. So this would be a 1 here. So now if we go back in, I think this works. 1 and for x, we get 1, 2 and for y, we get -8. -1 and for z, that's -2. Does this equal -9? And it does. So this would be 3 plus 2 minus 1. Does this really equal 4? And it does. And then -2 plus 6 plus 3. Does that equal 7? And it does. Yay. Okay, so just go back and substitute. To check. Okay, so again, see how it could have been really hard for me to go find that, or for you guys to find that, if I hadn't done the directions that we were doing. And then after all that work, it's good. I cringed when it didn't work, but it's good to go back and check your solution, because it is very easy to get, one slight thing off. But if you have all that concept right while you're doing it on an exam, you would get, most of your points. I would even prefer it and probably give you more points if you said, I checked this and it doesn't work. I don't see where it's going wrong. Okay, so let's see. look at one more. So let's say you were given first row is 2x minus 3y minus z equals 0. Then we have negative x plus 2y plus z equals 5. And then we have 3x minus 4y minus z equals 1. Okay, so I'm going to go back and just look. 2x minus 3y minus z equals 0. Negative x plus 2y plus z equals 5. 3x minus 4y minus z equals 1. So first write it as a matrix. And notice doing that we have 2, negative 3, negative 1, and 0. We have negative 1, 2, 1, and 5. And then 3, negative 4, negative 1, and 1. So column to column. So we need to get that 2 to be a 1. So multiple different ways that you can approach this. We can multiply everything through by 1/2, but then you have to deal with fractions. I could switch row 2 and row 1 and multiply row 2 by a negative, and that would make it a 1. I could add row 2 to row 1, negative 1 plus 2 would make a 1 where I want it. So it really doesn't matter which way you do it. If you do all the arithmetic right, then in the end you should get the same result. So let's just do row 2 plus row 1. So if I did that, technically I usually write down my rows I'm not changing. So negative 1, 2, 1, 5, 3, negative 4, negative 1, 1. And so now doing it, negative 1 plus 2 is 1. 2 minus 3 is negative 1. 1 minus 1 is 0. 5 plus 0 is 5. So we got the one where we want it. So we're going to use this row to get rid of the numbers below by multiplying it by the opposite of that coefficient. So basically here now, if we just take row 1 and add it to row 2. So row 1's the same. But now row 2 is 1 minus 1 is 0. Negative 1 plus 2 is 1. 0 plus 1 is 1. And 5 plus 5 is 10. So if we take negative 3 row 1 and add it to row 3. So negative 3 plus 3 is 0. Negative 3 times negative 1 is 3. 3 minus 4 is negative 1. Negative 3 times 0 is 0 minus 1 is negative 1. Negative 3 times 5 is negative 15. Negative 15 plus 1 is negative 14. Okay, so I got the 1 and 0s where I wanted in column 1, so moving to column 2. I already have a 1 where I need it. And I also notice if I add this row 2 to the row 1 above, that would make a 0. Same thing, add row 2 to row 3, that would make a 0 where we wanted it. So let's just rewrite row 2, 0, 1, 1, 10. And now we're looking at row 2 plus row 1. 0 plus 1 is 1. 1 minus 1 is 0. 1 plus 0 is 1. 10 plus 5 is 15. And then add row 2 to row 3. 0 plus 0 is 0. 1 minus 1 is 0. 1 minus 1 is 0. 10 minus 14 is negative 4. Okay. If you get a row of all zeros except for that last number, you're done. Technically, what this last row is saying for an equation is 0x plus 0y plus 0z is equal to negative 4. There's no way we can multiply any number by 0 and sum them up and get negative 4. This is impossible. So there's no solution to this system. If you are working with this and that last entry was also a 0, then it means something totally different. It means that you have a system that has more than one solution. So let's write that down. So note, if you get a row of all zeros in your matrix, when implying row operations, then your system has an infinite number of solutions. Okay, but you can't just stop there. You can't just say that it's an infinite number of solutions because that doesn't tell you anything about the solution. What you have to do is you're going to be able to manipulate each equation so that one variable is in terms of 1. So basically, I could have it where all my variables were in terms of x. So y was equal to something in terms of x, and z was written in something in terms of x. Or I could have everything in terms of y. So x could equal something in terms of y, and z could equal something in terms of y. And depending on which one you choose, one is usually easier than the other. It depends on what you arbitrarily choose for that variable, depends on what the rest of the variables will be. Okay, so maybe I can find one. Let's look at one. Okay, so we have a system. First equation is 2x plus y. And then we have is equal to negative 4. Second equation is negative 2y plus 4z equals 0. And we have 3x minus 2z equals negative 11. So 2x plus y equals negative 4. Negative 2y plus 4z equals 0. 3x minus 2z equals negative 11. Okay, so just be careful when you're setting this up. The coefficients. Notice that they're not all lined up where all the x's are in, the column y's and z's. So when you do that, just make sure that you keep it in order. And so our first row is going to be 2, 1. There's no z value, so 0, and then vertical line negative 4. Our second row, notice there's no x value, so put a 0 there. Our y value is negative 2. Our z value is 4, and then a 0. Our third row is 3. There's no y value, so 0, -2, and then -11. Okay, so column to column. We want a 1 here. Again, I can multiply by 1/2, but I don't like to deal with fractions. If all these numbers in this row were divisible by 2, I would do that. So I try to manipulate it without undoing something I've done previously, but this is the first column, so I'm okay. So notice that if we take, let's do, how would I write this? Let's look at row 3 minus row 1, right? 3 minus 2 is 1, and that would get us a 1 where we want it. So let's just do that real quick. So 3 minus 2 is 1. 0 minus 1, so that's -1. -2 minus 0, so that's 0. And -11 minus a -4. So -11 plus 4 is -7. So all my other rows were the same. 0, -2, 4, 0, 3, 0, -2, and -11. Okay, so we got a 1 where we wanted it and needed it. And so let's use that row to get rid of the numbers below. So if we look at -3 of row 1 and then add it to row 3, that would get us a 0 where we need it. So I'm only changing row 3. So -3 plus 3 is 0. -3 times -1 is 3 plus 0 is 3. -3 times this 0 is 0. Minus 2 is -2. -3 times -7, that's 21. 21 minus 11 is 10. Okay, so we're done with column 1, moving to column 2. So column 2, we want a 1 here. Okay, so I could sum row 3 to row 2, but I also notice that every number in row 2 is divisible by -2. So let's just multiply -1/2 times row 2. So that would give us 0, 1, -1/2 times 4 is -2, and -1/2 times 0 is 0. All the other rows stayed the same. Okay, so we want to get rid of the numbers above and below row 2. That one. So I notice if I look at row 2 plus row 1, 1 minus 1 would get us at 0. So we have 1, 0, -2 plus 0 is -2, and 0 minus 7 is -7. And if we look at -3, row 2 plus row 1. So -3 times 0 is 0 plus 0 is 0. -3 times 1 is -3 plus 3 is 0. -3 times -2 is 6. 6 minus 2 is 4. -3 times 0 is 0 plus 10 is 10. Thought this was supposed to be inconsistent. Nothing has canceled. This doesn't look like it's inconsistent. So I must have done something wrong. 2x plus y is negative 4, negative 2x plus 4z is 0, 3x minus 2z equals negative 11. Sorry, just check it. 3 minus 2, 0 minus 1, negative 2. Here it is. Eeks. It's back up here. Row 3 minus row 1, negative 2 minus 0. Right here, this should have been negative 2. Right, let me just check it again. Negative 2, okay, and this would have been, that's right. Okay, so it's only really when we're dealing with row 1, which we dealt with here. So negative 3, row 1, canceled. That here, this would have been a negative 2. So this here would have changed. So negative 3, that's 0. Negative 3 times negative 2 is 6. 6 minus 2, this would have been 4. That's a negative 2. Just make sure. So that would be negative 1/2. That still works. And we did row 2 plus row 1. So 0, 1, that's 0. Negative 2 plus negative 2. This would have been a negative 4 here. Still works. And then instead here, this would have been negative 3 plus 3 is 0. Negative 3 times negative 2 is 6. 6 plus 4 is 10. Is that right? And then 3, that's 10. I'm still not getting that it's a inconsistent. Because then I'm getting, from here, we can look at 1/10 times row 3, which gives me 0, 0, 1, 1. 0, 1, negative 2, 0, 1, 0, negative 4, negative 7. Now I can use this 1 to get rid of the numbers above. So I can do 2 row 3 plus row 2. So 0, 0, 1, 1. Row 2 now becomes 0, 0, oops, no, sorry, 0, 1, 0. 2 times 1 is 2 plus 0 is 2. And then I can do 4 row 3 plus row 1. So that would be 1, 0, 0. 4 times 1 is 4. 4 minus 7 is negative 3. So right now, it's not an inconsistent system. We have our solution, which we got right. X is equal to negative 3. Y is equal to 2. And Z is equal to 1. Although me thinking it was supposed to be an inconsistent system made me go back and look and found an error near the front. So, sorry about that. Okay, so let's take a break. And then we will look, if you want, we can go over another one. I kind of want to show you what would happen, but we can just look at an example of what it would look like and how to read the solution. Okay, so we're going to look at an example of what would have happened if you were working through and your matrix came up with a row of all zeros. And so if you had the following, first row would be 1, 0, 2, and your vertical line, -1. The second row is 0, 1, -4, -2. And our third row is all zeros. So 0, 0, 0, 0. Okay, so if this last entry in this last row was not a 0, then, and it was a number other than 0, and you had zeros everywhere else, then we know there's no solution. But if you get a row of all zeros, then this means it's a dependent system, and there's an infinite number of solutions. So let's go back and rewrite what each row is in terms of equations. And so this first row, this would be our x values, column y, column z column, and this is what it's equal to. So our first row would be x plus 2z equals -1. And then our second row would be y minus 4z equals -2. So we want to rewrite each equation or each variable in terms of one other variable. I notice here that the first equation has z in it and the second equation has z in it. So we want to rewrite, it would be best if we rewrite x in terms of z and y in terms of z. So if we solve for x here, we would just subtract 2z on both sides of our equation, and we would get x then is equal to -2z minus 1. And if we solved for y in the second equation, we would add 4z to both sides, and so we would get y then is equal to 4z minus 2. So our solution is dependent in this case on what you choose z to be. And so our solution would be the point, our x value is -2z minus 1. Our y value of our point is 4z minus 2. And our z value is just z. So notice there's an infinite number of solutions that would go back and work. It just depends on the z value again. So if you let z equal 0, your solution would be, well, -2 times 0 is 0 minus 1. So you'd have -1 for the x value. You plug in 0, you have to put it in for everything though. 0 in for your y. You'd have 4 times 0, 0 times, or plus -2, so minus 2, 0. So anything, there's an infinite value you can choose for z, dependent on z, x, y, and are dependent on what you choose z to be. So if it was -1, if it was 1, we get -3 for our first term. 4 times 1 is 4 minus 2 is 2 for our second term, and z was 1. If it's an independent system, those are the ones that we've pretty much looked at so far, then we always have a value, one value that falls out for x, y, and z. Okay, so I thought for the next example, we'll look at an application, and you can see where matrices are kind of helpful in keeping the data organized. So bear with me, let me read through this, and then we'll start rewriting things in, and then writing out equations. Okay, so you have a dietitian at a general hospital wants a patient to have a meal of 47 grams of protein, 58 grams of carbohydrate, and 630 milligrams mgs of calcium. The hospital food service tells the dietitian that the dinner for today is pork chops, corn on the cob, and a 2% milk. Each serving of pork chop has 23 grams of protein, 0 grams of carbohydrates, 10 milligrams of calcium. Each serving of corn on the cob has 3 grams of protein, 16 grams of carbohydrates, and 10 milligrams of calcium. Each glass of 2% milk contains 9 grams of protein, 13 grams of carbohydrates, 300 milligrams of calcium. So how many servings of each food should the dietitian provide the patient? Okay, so they want to know, and usually this kind of clues you in which ones to choose the variables. It wants to know how many servings of each food. And so we can have maybe X equal the number of servings of pork chops. We can let Y equal the number of servings of corn. And Z equal the number of servings of milk. Okay, and so we also know that our pork chops corn, and we have milk, and we're looking at the following of each. And we need a total. We have totals that we need are of protein, carbohydrates, carbs, and calcium. Okay, so let's just go through and pick out the protein for all of these items. Or I guess we could go through pork chops and just list it through the row. Maybe that might be easier. The totals, so total down here of protein that is needed is 47 grams. 58 grams of carbohydrates. And then it was 630 milligrams of calcium. So that was what this patient needed. And so going through pork chops, they have 23 grams of protein, 0 grams of carbohydrates, and 10 milligrams of calcium. Corn on the cob has 3 grams of protein, 16 grams of carbs, and 10 grams of calcium. And each glass of milk has 9 grams of protein, 9 grams of protein, 13 grams of carbohydrates, and 300 milligrams of calcium. So we pretty much have our equation or our system all set up. So for protein, for pork chops, there's 23 grams, so 23x, plus for corn, there's 3 grams and so times y, plus 9 times z. This has to equal a total where they need 47 grams of that protein. So now our next equation is going to be this column. So 0 carbs, so 0x, I don't have to write that, 16y plus 10z equals, oops, sorry, wrong way, this way. I could have written it where I transposed my columns and rows. I should have. Okay, so here it was 0x plus 16y plus 13z equals 58. And then this one, this row or column gives us 10x plus 10y plus 300z equals 630. And I don't like that. I don't have a 1 in front of my x, and I don't like that. If I multiply through, ooh, yay. I see it. Let's say, so here's our system. Let's rewrite it as a matrix. Notice that we can multiply this third equation by 1/10, and that would get me a 1 in front of my x, which I want. So let's do 1/10 times row 3. We haven't swapped yet. And so I'm going to just do these arrows back and forth to row 1. So my row 1 is now going to be my row 3, and my row 1 is now going to be is my row 3, and my row 3 here is going to be 1/10 of that is my row 1. So let's just write that out. So if I multiplied each coefficient by 1/10, that would have given me a 1. 1/10 times 10 is a 1. 1/10 times 300 is 30. My line, and 1/10 times 630 is 63. My second equation, my second row, no x, so 0, 16, 13, and then 58. And then my third row, which was my first equation, is 23, 3, 9, and 47. Okay, so I kind of manipulated it first before I wrote my matrix. Now let's use where we got the 1 where we wanted it to get rid of all the entries below. And so if we look at negative 23, row 1, and add it to row 3. So row 1 is the same. I'm just going to rewrite it, 1, 1, 30, 63. Row 2 is the same, 0, 16, 13, 58. So negative 23 plus 23 is 0. Negative 23 times 1 is negative 23, plus 3 is negative 20. Negative 23 times 30. Ooh, let's see. Plus 9 is negative 681. Negative 23 times 63 plus the 47 down below. That would give us negative 1,402. I'm just checking my work, guys. Okay. So I now got my, I don't see anything wrong. And I guess I could go back. Let me just check. Okay, so now I need to make this a 1. I'm not seeing any way to make this a 1 that's easy other than multiplying through by 1/16. And I don't like that that is not going to be a fraction. Anyone see an easier way? Okay, well then we got to deal with fractions. So 1/16 times row 2. So if I do that, I get 0, 1, 13 over 16, then 58 all over 16. So I need to use this row 2 now to get rid of the numbers above and below. So if I had to look at negative row 2 plus row 1, that would do it. So 0, and let's just rewrite this, 0, 1, 3, 13/16, 58/16. Okay, so 0 plus 1 is 1, negative 1 plus 1 is 0. This is where it's going to get messy. So this is going to be a negative 13 over 16. Where am I going to put it? Negative 13 over 16. I'm going to need to add it to 30, but I need a common denominator. So 30 times 16. That's 480 over 16. If I add that to a negative 13, so minus 13, this gives me 467 over 16. So now I'm taking negative 58 over 16 and adding it to 63. So negative 58 over 16 and adding it to 63. So I need a common denominator again. So 63 times 16, that gives you 1,008 all over 16. And so now if I sum that, so minus 58, that would get us 950 over 16. So now I need to get rid of this negative 20 in row 3. So if I do 20 row 2 plus row 3. So I get 0, 0. So 20 times 13 over 16. And then what do I have to do? Minus 681. Yeah, minus 681. So I need a common denominator, 16 over 16. So that's 20 times 13 is 260. 681 times 16 Where's that 6? Is 10,000, so minus 10,896 over 16. That would give us a negative 1,000 or 10,636 over 16. And then we're looking at 20 times 58 over 16. All plus negative 1402 over 16. Times 16 over 16 to get a common denominator. So this is 1,160 over 16 minus 22,432 over 16. Which equals negative 21,272 all over 16. Okay, yuck. So you could see where maybe I was cringing when I was looking at this, because I knew that it could get really ugly, and this is where errors could happen really easily. So we're done with column 2. We gotta now move to column 3. There's only one way to make this entry in the third row, third column 1, and that's just to multiply by the reciprocal. And so if I multiply this row 3 by that reciprocal, so I'm going to multiply it by negative 16 over 10,636. Okay, so my row 1 is all the same. 1, 0, 4, 6, 7 over 16, and then 950 over 16. There's a reason I kept everything. I could reduce here, but if I reduce, then they're not all the same denominator, and it's easier to keep them the same denominator, so I don't have to go back and get common denominators. My second row is 0, 1, 13 over 16, and then I have 58 over 16. So multiplying through by the reciprocal of this third row, third column, I get 0, 0, 1. And so the reason I was cheering, I don't know if you heard it under my breath, but that 10,636 actually goes evenly into this 21,272. It goes in exactly 2 times. Notice our 16s cancel. Negative and a negative is a positive, and so we just get back 2 here. So now I need to get rid of the entries above that third row, third column. And so I'm just going to multiply by the opposite of what this is. So when I sum it, it goes away. My row 3 is staying the same. My new row 1, well, if I look at negative 467 all over 16, row 3, and I add it to row 1. Well, my first 3 entries are nice, 1, 0, 0. So I need to do a little work here. I'm going to multiply this by 2 and add it to the 950. So if I look at the 2 times 467, that's 934. So I would have 934 over 16, and that would be negative, plus 950 over 16. So that gives us 16 over 16, which is 1. And one more, get rid of the 13 over 16. We can multiply row 3 by negative 13 over 16. Row times row 3 plus row 2. So we have 0, 1, 0. Okay, so negative 13 sixteenths times 2. That's negative 26 sixteenths. Plus a 58 sixteenths. This is 42 sixteenths. Oops. Is that right? Did I do that right? It's 32. So 32 over 16, which is 2. So now we can read this off. X is equal to 1, but remember we chose X to be the number of servings of the pork chops. Y was equal to the number of servings of the corn, and Z was the number of servings of the milk. So this patient can get 1 serving of pork chops. They get Y is equal to 2, so they get 2 servings of corn. And Z is also equal to 2. And so that would be 2 servings of milk. Okay, so wasn't the prettiest. We made it through though. We could go back and we could check our work. It should come out that if we put in 1 serving, 2 servings, and 2 servings, so 1, that's 23, plus 6 is 29, 29 plus 18 is 47. If we plugged it in here, well, there's no protein. 2 times 16 is 32. 32 plus 26 is 58. And I'm sure it would work for the third equation, so you can check that if you like. So that is systems of equations. I want to go back. We're going to jump. We have 2 more sections left in this chapter in this book, which is 2.7. So this would be nonlinear inequalities, systems of inequalities. And then tomorrow we're going to look at partial fraction decomposition. So basically, let me just tell you about that. It's kind of cool. It was one of my favorite things in calculus too. So basically it's taking this really complicated fraction and being able to rewrite it as a sum or difference of simpler fractions that will be easier to work with later on. So a lot of times, you know, we tend to go one direction in math for a while, but it's actually good to be able to go back and forth. Let me pull another page. So this non-linear systems of inequalities is a lot easier than what we were just doing if you're good at graphing. And this will also give us some review on graphing some conic sections. And so this systems of inequalities. So when we're solving these systems of inequalities, we're trying to figure out the same region that they overlap, each inequality has in common. Before we do that, let's just look at graphing just an inequality with more than one variable. So for instance, if you looked at x squared plus y squared is less than or equal to 9. So it's always easiest if we just graph what this would look like as if this had been an equal sign. If there is a less than or equal to or a greater than or equal to, the graph of the equation is going to be a solid line. And then if it is strictly less than or strictly greater than our inequality, then it's going to be a dotted line. So any point on that line of the graph would not be part of the solution if it was dotted. If it's solid, it is part of the solution set. So if you look at this and we just looked at x squared plus y squared equals 9, that should look familiar. And you should hopefully notice right away that this is a circle. The center is at 0, 0. And our radius is, this is r squared on the other side. 9 equals r squared, so our radius is equal to 3. So if we graph that, determine if you want it dotted or a solid line. We have the equal to part of the solution, and so we're going to make it a solid line. And so if we graph this, go up, down, left, and right 3 from our center, and get this circle. So any point on this circle is a solution, but we also have to determine which area to shade. So you're either going to shade everything outside of the circle or everything inside of the circle. And one of those is going to make this statement, this inequality, true all the time. And so if you can't see where to shade, then choose a test point. So if I chose a point anywhere, so I think it's going to be inside. If I choose a point inside the circle and I test it, and it's a true statement, then that's the region I need to shade. So notice if I plug in the point 0, 0, so x is 0 plus y is 0. So 0 plus 0, is that less than or equal to 0? I'm sorry, less than or equal to 9? Yes, it is. If I had chosen a different value, so let's say I had chosen the point when x is 4 and y is 0. Well, this would give me 4 squared, which is 16. 16 plus 0 is 16. Is 16 less than or equal to 9? No. So no point outside of this region would have worked. And so my solution is going to be everything inside of this and the circumference. Let's say you had y is greater than x squared plus 2. So we want to graph y equals x squared plus 2 and determine if you want your graph to have a solid or dotted line. This is strictly greater than, so we know it's going to be a dotted line. We should be able to bring in our techniques of graphing that we used in this class. So this is the graph of x squared. This plus 2 is shifting it up 2 units. Or you can think of it as in vertex form, where our h value is 0 and our k value is 2. Oops, and this has to be a dotted line. And so now we need to determine where to shade. And this was saying that it is greater than, it's greater than, strictly greater than that. So let's choose a point. So maybe 0, 0 is always a good point if it's not on the graph itself. And so if we plugged in 0, 0 into this, we want to see if it's a true statement or not. So is 0 greater than 0 squared plus 2? This is a false statement. And so this was not going to be part of my solution outside of the parabola. It should be, and any point I choose that is inside this parabola should work. So maybe let's just test it anyways to show it. But here's a point that's inside the parabola shape, and this was when x is 0, y is 3. We plug those values in, we get 3. Is this greater than 0 squared plus 2? And it is, that's true. So I know that the area that's going to be any point inside this parabola will be part of my solution set. And so there's an infinite number of values that work. So that's kind of a review of graphing inequalities, nonlinear inequalities. But now with the systems of inequalities, so you're going to have multiple inequalities, and we have to figure out where do those areas where they're both shaded overlap. And the area where they both are shaded is going to be your solution. Sometimes it's helpful to be able to find those points of intersection, and we've been doing that and just found the tools to do that with solving nonlinear equations. Let's see if I can pull some up. So I'll graph each of the following inequalities. Let's see, you had the first equation or inequality is x squared plus y squared is less than or equal to 25. And the second one, that one is y is greater than, less than or equal to x squared minus 5. Okay, so you want to graph each one like there was an equal sign. Determine if the graph of that line is going to be solid or dotted, depending on your inequality. Those are both going to be solid because they both have the equal to part. You should be able to recognize again the shape of the graph. So x squared plus y squared equals 25 is just a circle with a radius of 5. So we're going to go up, down, left, right, 5. And we're going to have a solid line. So this is where I do not shade all of what I'm going to have until the very end. But I do kind of give myself direction on where to shade. So this tells me less than or equal to 0. So I know it's everything inside of that circle. So I'm just going to put little arrows to myself, telling myself that I'm going to be shading inside the circle. That's part of the solution just for that green inequality. So now if I look at y is less than or equal to x squared minus 5, I recognize that this is a parabola. I notice that this is x squared, just shifted down 5 units. So I have a point here. When I choose, let's see, any other points that we know? Well, we can plug in values. If I plug in 1 in for x, that would give me 1 squared minus 5, which is negative 4. So I have a point here, I have a point here. If I plug in 5, well, that's going to be way up here. I'm not sure where it intersects, but let's just get some sort of idea. And we can find these values. We can, again, we can look at that in a minute. That would be good review too. Okay, so looking at this tells me it's everything that is less than or equal to x squared minus 5. And so if I didn't know, I would choose a point where to shade. And so if I chose 0, 0, is 0 smaller than 0 minus 5? It is. So I'm going to shade everything for this parabola inside. So if we think about where these two colors or where these both would interlap if we had done it, notice that it's everything that's kind of inside that parabola, but also inside the circle inside the parabola. So our solution is going to be this area in here. So everything on this line, everything in here, and everything in here. So let's find these points of intersection, and that's kind of a review of what we covered yesterday. So find where x squared plus y squared equals 25 and y equals x squared minus 25 intersect. So looking at the graph, we should get 3 answers back. We should get one that's on the y-axis below the x-axis, and we should get one in quadrant 1 and one in quadrant 2. This is basically just doing a nonlinear systems of equation. And so you have to determine which way you want to solve this. This we can use, it's in the form that we can use this substitution method. We know what y is in terms of x. So if we go back and plug in what y is in terms of x into that first equation, you're left with x squared plus, you see a y there, we're going to rewrite it. That, put a parentheses, quantity squared equals 25. Okay, so I can't just, I have to expand this and combine like terms and try to factor and solve. So this is x squared plus, so x squared minus 25 times x squared minus 25. Well, x squared times x squared is x to the 4th. But then I'm going to have a negative 25x squared and a negative 25x squared. So that's going to be a negative 50x squared. And then I'm going to have a negative 25 times negative 25. So 25 squared gives us 625. So plus 625 equals 25. So I have an equation that kind of can be manipulated to look like a quadratic. So let's kind of rewrite it to get everything to one side of the equal. And so I have an x to the 4th term. I have an x squared minus a 50x squared is a negative 49x squared. I'm going to subtract 25 on both sides, so this gives me plus 600 equals 0. You think of two numbers that multiply, you might be faster than me, to 600 and add to a negative 49. Okay, so let's see. So 20 and 3, 30, that's not going to work, right? This is where kind of breaking it down as factors is helpful. This is 60 times 10. 60 is 6 times 10. 10 is 2 times 5. 10 is 2 times 5. 6 is 2 times 3. So 600 written in prime factors are 1, 2. There's 3 2's and 1 3 and 2 5's. We know that they both have to be negative. Oops, 2 5's, not a 55. Because we're multiplying to get a positive, adding to give a negative. So what about grouping 25? This would be 2 times 2 times 2 is 8 times 3 is 24. A 24 and a 25, both of them negative. That would work. Okay, so we just found the factors. So I can factor this as x squared, because this is next to the fourth function, minus 25, and x squared minus 24 equals 0. So I can set each factor equal to 0 and solve. So x squared minus 25 equals 0, and x squared minus 24 equals 0. And so square root method would be the easiest, or factor that this is plus or minus the square root of 25. If I add 25 to both sides and take the square root, so this is x is equal to plus or minus 5. If I do the same thing here, I get x is equal to 24. Sorry, x squared equals 24. Take the square root. So this is plus or minus the square root of 24. Okay, so for now I'm going to leave it like that, or actually when I plug it in, but for now, let's pull out what we have a factor of. 24 is 4 times 6. 4 is a perfect square. Square root of 4 is 2, so this is 2 root 6, plus or minus. This is our x value. We need to figure out what y is. So we want to find what is the y value if x is plus or minus 5 or plus or minus 24. It would be easiest if we looked at that second equation because it's already in that form, y equals. So we have y equals, but you could plug it into either equation and determine. I feel like something's wrong. If we plug in x equals 5, actually maybe not. If we plug in x equals 5, we get 5 squared minus 25, which is 0. So when x equals 5, y is 0. So we have a point at 5, 0. And then if we plug in negative 5, so if x equals negative 5, plug it in. Negative 5 squared is 25. 25 minus 5 is 0. So at negative 5, we get 0. If x is equal to plus or minus root 24, this would give us y is equal to plus or minus root 24 quantity squared and then minus 25. But if you square the square root, well, the negative and positive, that would just be 24 minus 25. So y is equal to negative 1. Okay, so remember I said that there could be an extraneous solutions. And so this might be a case where there is. My graph could be off. Let's see. X is 0, y is 5. This doesn't look right. Because this is, something's off. If I plug in 5 and 0, that works. And if I plug in -5 and 0, that works. That works.
The beginning where it's the find where x squared plus y squared equals 25. And is it supposed to be y equals x squared minus 5?
Aha.
The equations they intersect.
Darn it. Yes, that's where it is. So I knew something's going on. I'm noticing that something's off. So this right here, this should have been -5. This would have made this a lot easier, but this was at the beginning. So it would have plugged this in. Let's see. This would have been x squared plus y squared, but y squared would have been that x squared minus 5 instead of 25 is equal to 25. So here we have x squared, this foiling this, oops, this quantity squared. So foiling this out, we would get plus x to the 4th minus 10x squared plus 25 equals 25. So now getting this over to the other side, the 25, that's going to cancel our constant. So we have really just x to the 4th, x squared minus 10x squared is -9x squared equals 0. Notice you can factor out an x squared. So this would have given me x squared minus 9 equals 0. Difference of squares, x minus 3x plus 3 equals 0. So x is equal to 0, x is equal to 3, and x is equal to -3. This looks much better. Now, if we go back and we plug in, but we're not plugging it into y squared minus 25, we're plugging it into y equals x squared minus 5. If you plug in 0 here, then you get 0 minus 5, which is -5, y equals -5. So we have a point at 0, -5, which we already knew. And then if we plug in x equals 3, so we get, where do we get? 3 squared is 9, 9 minus 5 is 4. So this point here is at 3, 4, so 1, 2, 3. And it looks about 3, 4. And if you plug in -3, well, you're squaring it, so you're going to get the same value, and there's no other term of x, of y equals 4. Yay. Okay, so here is a problem that can show me that you can graph certain things, you know how to solve nonlinear systems, and you know how to do inequalities, systems of inequalities. So here's a problem that's kind of hitting a lot of target areas that we covered for this test in one question. Oops. Okay, we almost did it. Like I said, and we're where I want to be. We have only 4 more sections for this course. The partial fraction decomposition, and then we have sequences and series, which is 13.1, 13.2, and 13.3 in our textbook. So our test is on Thursday And we'll do some stuff tomorrow on the partial fraction decomposition. And then I think I will review for the rest of the period. You'll take the test Thursday. It will be on a PDF. You need to come in with a webcam while you're taking the test. It has to be on while you're taking the test, or you won't get points. And I can give you more details tomorrow. What else? Okay, let me, but I think that's it on the details. Let me stop the recording and then for the day, and then I can answer questions.